Somewhere inside a lab cooled colder than deep space, a machine just did something no artificial intelligence on Earth has ever managed. And the scientists who watched it happen are still trying to figure out what it means for everything we thought we knew about computing. For years, we've been told a simple story. Artificial intelligence is the technology of our time. It writes, it paints, it diagnoses disease, it drives cars, and it seems to improve every single month without slowing down. We've watched language models go from clumsy chatbots to systems that can hold a conversation, summarize a research paper, or generate working computer code in seconds. It has felt at times like AI has no ceiling, like there's nothing it cannot eventually learn to do if you simply give it more data and more computing power. But that story has a quiet flaw in it, one that most people never hear about, because it doesn't fit neatly into a headline. AI, no matter how advanced, is still built on classical computers. It still processes information as ones and zeros, one instruction after another, even when it looks like it's doing many things at once. And there are certain problems, certain categories of computation, where that architecture simply hits a wall. Not a soft limit that better engineering can fix, a hard mathematical wall. This is where quantum computing enters the story, and it enters not as a competitor trying to catch up to AI, but as something fundamentally different, a machine that doesn't think in ones and zeros at all. To understand why this matters, you have to understand, even briefly, what makes a quantum computer so strange. A classical computer, the kind sitting in your pocket or powering the largest AI models in the world, stores information in bits. Each bit is either a 0 or a 1, nothing in between. A quantum computer stores information in qubits, and a qubit can exist as a 0, a 1, or something called a superposition, which is essentially both at the same time until it's measured. On its own, that sounds like a neat physics trick, not a revolution. But when you link many qubits together through a phenomenon called entanglement, something happens that classical machines cannot replicate no matter how much hardware you throw at them. The number of states the system can represent grows exponentially, not linearly. A system of just a few hundred entangled qubits can represent more possible states than there are atoms in the observable universe. This is not an exaggeration. It's a mathematical consequence of how superposition and entanglement scale. And it means that for certain types of problems, a quantum computer isn't just faster than a classical computer. It's operating in a different category of computation altogether. For a long time, this remained mostly theoretical. Quantum computers existed, but they were fragile, error-prone, and limited to toy problems that didn't matter much outside of physics departments. Skeptics, and there were many, pointed out that quantum computers were solving contrived math problems with no real-world use, while AI was out here changing how people work, communicate, and create. That skepticism was reasonable. For years, it was justified. But recently, the gap has started to close. And in a few specific, well-documented cases, quantum systems have started doing things that classical AI, running on classical hardware, genuinely cannot do, not efficiently, and in some cases, not at all. Let's start with one of the clearest examples, because it strikes right at the heart of AI itself. Researchers working with an IBM quantum computer set out to test something bold. Could a quantum processor actually improve a language model, the exact kind of AI system behind the chatbots and writing tools millions of people now use every day? They built a hybrid system, encoding part of the model's internal structure, specifically components called Cayley unitary adapters, directly onto the quantum hardware. Then they trained it and compared its performance to a purely classical version of the same model. The quantum-enhanced version didn't just perform on par with the classical model. It answered questions correctly that the classical version got wrong. The researchers measured a 1.4% reduction in what's called perplexity, a metric that essentially measures how well a language model predicts and understands text. That might sound like a small number, but in the world of language models, incremental gains like that are exactly what separate breakthrough systems from mediocre ones. What's remarkable isn't just that the quantum version performed better, it's why. The lead researcher explained that this result demonstrates a clear path forward for building quantum hybrid AI systems, and that it could help researchers overcome a real bottleneck in the field, one where progress is increasingly limited not by ideas, but by the sheer physical scale of the classical computing infrastructure needed to keep pushing AI models bigger. In other words, we may be approaching a point where making AI smarter isn't about stacking more classical chips into bigger data centers. It might be about handing certain calculations off to a fundamentally different kind of machine, one that can represent and process information in ways classical silicon never could. Then there's the example that made headlines across the tech world for a different reason entirely, because it wasn't about improving AI. It was about raw computational dominance. Google's quantum processor, a chip known as Willow, built with 105 qubits, was set loose on a task specifically designed to showcase quantum advantage. The results stunned even people who work in the field. Willow completed the computation in just over 2 hours. running the same task on one of the most powerful classical supercomputers on the planet, the kind of machine that consumes enormous amounts of energy and fills entire warehouses, was estimated to take 3.2 years. Not 3.2 years because engineers hadn't optimized the code well enough. 3.2 years because that is roughly how long the underlying math requires when you're limited to classical bits, processing information sequentially. Willow finished the same task about 13,000 times faster. Now, it's worth being honest about what this particular benchmark represents. It was a task engineered to highlight where quantum computers excel, not a general-purpose measure of intelligence or usefulness the way we might judge an AI model. But the significance isn't really about that one task. It's about what it proves is possible. It demonstrates with hard experimental evidence that quantum computers aren't just theoretically superior for certain calculations. They are right now superior in practice, by a margin so large that no amount of classical hardware scaling could ever close the gap. That's not a temporary lead. That's an entirely different growth curve. Because here's the part that should genuinely change how you think about all of this. Classical computing power, including the AI systems built on top of it, tends to scale in predictable, roughly linear or polynomial ways. You want a model twice as capable, you generally need something in the ballpark of twice the data, twice the compute, sometimes more. Quantum computing, for the right category of problems, scales exponentially, which means the gap between quantum and classical systems doesn't stay constant as problems grow larger. It widens, and it widens quickly. A modest classical head start can be erased in a matter of a few additional qubits. This is the mathematical reason why so many researchers are convinced that certain problems will always remain out of reach for classical AI, no matter how many years of engineering improvements we throw at it, and why quantum computing isn't just another incremental upgrade. It's a different kind of ceiling breaker entirely. But raw speed on a single benchmark task is only part of the story. What's arguably more interesting is what happens when quantum computing gets applied to the exact kinds of messy, chaotic, real-world problems that AI models genuinely struggle with. Researchers at University College London set out to test whether combining quantum computing with AI could improve predictions of chaotic systems, the kind of wildly sensitive, hard-to-model behavior you find in weather patterns, turbulent fluids, or complex biological processes. Chaotic systems are notoriously difficult for classical AI to predict accurately over long stretches of time because tiny errors compound rapidly. Classical models tend to drift away from reality the further out they try to forecast. The UCL team let a quantum computer identify hidden patterns within the data first, patterns that were then fed into the AI model. The result was an AI system that became noticeably more accurate and dramatically more stable over long prediction windows. And it did this while using far less memory than standard classical approaches required. Think about what that actually means. The AI wasn't just given more data or more training time. It was given a fundamentally different lens through which to view the data first, a lens only a quantum processor could provide. And that alone was enough to outperform what classical methods could achieve on their own. The implications stretch well beyond academic curiosity. Climate scientists trying to model long-term weather systems, energy companies trying to predict fluctuating grid demand, and medical researchers trying to model the unpredictable progression of disease could all benefit from AI systems that finally have a reliable way to handle chaos instead of being defeated by it. There's also a quieter, more technical breakthrough happening in research circles that deserves attention because it strikes at something even more fundamental than speed. It's about what quantum computers can represent that classical machines structurally cannot, at least not without an absurd amount of resources. Physicists working on foundational machine learning tasks, things like high-dimensional linear classification and dimensionality reduction, the kind of math that underlies how AI systems make sense of massive, complicated datasets, have established what researchers are calling provable quantum supremacy in these areas. That word provable matters enormously here. This isn't speculation or a promising early result. It's a mathematically demonstrated advantage. Here's the key insight behind it. Every time scientists run a complex physical experiment, whether it's in particle physics, chemistry, or material science, that experiment generates a staggering volume of raw data. With a quantum computer, researchers can compress and process that entire flood of information directly on a tiny quantum chip, extracting the meaningful patterns in a single run. A classical machine, without that same quantum compression, would need something entirely different to keep up. Massive energy-hungry data centers built specifically to store the raw information, and even then, without the quantum system's ability to extract clean signals from a single pass, researchers would be forced to repeat the same expensive, resource-draining experiment over and over just to approximate what the quantum machine captured the first time. This is a genuinely different kind of advantage than raw speed. It's an advantage in representation itself, in the very ability to hold and make sense of information efficiently. And it's one of the clearest, most rigorously proven examples of a case where classical AI, no matter how well engineered, is running into limits that aren't about better algorithms or bigger budgets. They're limits baked into the mathematics of classical information itself. It's worth pausing here to ask why this took so long to happen, because for most of quantum computing's history, the field was defined more by promise than by proof. Physicists have talked about the theoretical power of quantum computers since the 1980s, when the idea was first proposed as a way to simulate quantum systems that classical computers simply couldn't handle. For decades afterward, progress was measured in tiny increments, a few more stable qubits here, a slightly longer coherence time there, incremental gains that excited specialists but meant almost nothing to the outside world. Meanwhile, classical computing kept doubling and doubling again, and AI rode that wave to become the most visible technological story of the last decade. It's easy to understand why so many people assumed quantum computing would remain a permanent footnote, an interesting idea that never quite made the leap from physics lab to practical tool. What changed wasn't a single dramatic discovery. It was the slow, unglamorous work of error correction, of learning how to keep fragile qubits stable long enough to actually compute something meaningful, of building control systems precise enough to manipulate particles at temperatures colder than outer space, without losing the information stored inside them. Each of those engineering victories individually looked minor. Stacked together over years, they eventually crossed a threshold, the threshold where quantum computers stopped being toys for physicists and started being tools capable of outperforming classical machines on real, meaningful tasks. That threshold is exactly where we find ourselves now, and it explains why so many of these breakthroughs are clustering together in such a short window of time. We're not seeing gradual, isolated wins. We're seeing what happens when years of incremental engineering finally compound into something the outside world can actually notice. It also explains why the tone among serious researchers has shifted so noticeably. A few years ago, most experts in the field spoke carefully, almost defensively, about quantum computing's potential, always hedging their claims with reminders that practical applications were still years, maybe decades away. Today, that caution hasn't disappeared entirely, and it shouldn't, but it's being paired with a new kind of confidence, the confidence that comes from having actual experimental results to point to instead of just theoretical arguments. When a researcher can say, with data in hand, that a quantum-enhanced model answered questions a classical model got wrong, or that a quantum processor finished in 2 hours what would have taken a supercomputer 3 years, that's a fundamentally different kind of claim than saying quantum computers might someday be useful. It's the difference between a promise and a receipt. And receipts are exactly what have been piling up recently, from IBM's quantum-trained language models, to Google's Willow processor, to the chaos prediction work coming out of UCL, to the provable advantages being documented in foundational machine learning tasks. Each one, on its own, might be dismissed as a narrow, specialized result. Together, they start to look like a pattern. And patterns are how paradigm shifts usually announce themselves, quietly, piece by piece, until one day people look up and realize the ground has already shifted beneath them. Now, it would be misleading to tell this story as if quantum computing has simply left AI in the dust, because the relationship between these two technologies is far more interesting than a simple rivalry. In fact, some of the most exciting recent progress hasn't been quantum computers replacing AI at all. It's been AI making quantum computing dramatically better, faster than anyone expected. Researchers working on some of the most important algorithms in quantum computing turn to AI systems to help them search for improvements, essentially letting the AI try thousands of different theoretical approaches at a pace no human team could match. What happened next surprised even veteran physicists in the field. The AI combined past scientific results in genuinely novel ways, showing an understanding of niche, highly specialized subdisciplines within quantum computing as it worked through thousands of possibilities. One of the researchers involved admitted that without the AI's help, his team likely would have tried a handful of ideas, watched them fail, and quietly concluded the whole approach simply wasn't possible. Instead, the AI's proposals ended up significantly improving some of the field's most important algorithms. A senior researcher on the project, a widely respected pioneer in quantum computing, expressed genuine surprise at how much the AI was able to reduce the number of qubits required for certain calculations, a detail that matters enormously because fewer required qubits generally means a more practical, more achievable quantum computer. Importantly, the humans didn't step back and let the AI run wild. They spent months carefully verifying every result the AI produced before trusting it enough to publish. The researchers remained firmly in control of the process, asking the right questions and guiding the AI toward genuinely useful answers, rather than simply accepting whatever it produced. This is perhaps the most honest way to understand where we actually stand right now. It's not AI versus quantum computing. It's AI and quantum computing, each helping to push the other past barriers that neither could clear alone. And that partnership comes with a warning attached, one that researchers are taking increasingly seriously. Because if AI can help accelerate the development of practical quantum computers, it can also accelerate the timeline for something far more disruptive. Quantum computers powerful enough to break the encryption that currently protects almost everything digital, from banking systems to private messages to national security infrastructure. Experts studying this intersection have pointed out that the arrival of a sufficiently powerful quantum computer, arriving sooner than many expected because of AI-assisted research, could expose nearly every system in the world to a quantum-capable attacker. The reason quantum computers are so disruptive to encryption comes back to that same exponential scaling that makes them so powerful for other tasks. Many of the encryption methods protecting our data today rely on math problems that would take classical computers, even the fastest ones, thousands of years to crack. A sufficiently advanced quantum computer could potentially solve those same problems in a fraction of that time. This is precisely why so much current research is also focused on something called post-quantum encryption, new cryptographic methods specifically designed to remain secure even against a quantum attacker. It's a race that most people never hear about, running quietly in the background while the public conversation stays focused on flashy AI chatbots and image generators. Of course, none of this means quantum computers are about to replace AI or that they're sitting on desks solving your everyday problems anytime soon. It's important to be honest about where the technology actually stands. Quantum computers remain extraordinarily fragile machines. Qubits are famously delicate, easily disrupted by the smallest environmental interference, even something as seemingly irrelevant as cosmic rays reaching the chip from outer space. To compensate for this fragility, researchers spread information across many physical qubits to create a smaller number of stable, reliable ones, a process called error correction. In some current approaches, it can take anywhere from 100 to 1,000 physical atoms just to reliably encode a single stable qubit. That gives you a sense of just how much overhead is still required to make these systems dependable. Scientists themselves are careful to caution that practical, large-scale quantum computing remains very much an active area of research, and that many headline-grabbing claims about quantum breakthroughs deserve careful scrutiny and independent verification before anyone gets too far ahead of the actual evidence. The examples we've walked through here are real, they're documented, and they represent genuine, measurable cases where quantum systems outperformed what classical AI could achieve on its own. But they are narrow victories, specific tasks, where the unique mathematics of quantum mechanics happens to align perfectly with the problem at hand. They are not evidence that quantum computers have somehow become smarter than AI in some broad, general sense. Nobody serious in the field is claiming that. What they do represent is something arguably more important than a single dramatic victory. They represent proof of concept, proof that the walls classical AI runs into aren't always failures of engineering or a lack of enough data. Sometimes there are structural limits built into the very nature of classical computation itself, limits that can only be broken by fundamentally rethinking how information is processed at the physical level. And once you accept that, the future starts to look less like a battle between two competing technologies and more like the layered, cooperative future that researchers keep describing when you ask them directly. Quantum processors handling the specific calculations that are exponentially hard for classical machines. Classical AI handling everything else, the broad reasoning, the language generation, the pattern recognition across massive everyday data sets, the tasks it was already excellent at. And increasingly, systems where the two work together in the same pipeline. Quantum hardware, feeding cleaner signals and richer representations into AI models that then use that information to make better predictions, better decisions, and better discoveries than either technology could manage alone. Think about what industries stand to change if this trajectory continues. Drug discovery, where researchers currently spend years and billions of dollars simulating how molecules might interact, a problem that scales so explosively in complexity that classical computers can only approximate the answers, is exactly the kind of high-dimensional, exponentially complex problem quantum systems are suited for. Materials science, where discovering a new superconductor or battery material means exploring an almost unimaginably large space of possible atomic configurations, faces the same fundamental barrier. Financial modeling, where firms are already exploring quantum computing for portfolio optimization and risk analysis. Problems where the number of possible combinations grows so quickly that even the world's fastest classical supercomputers eventually run out of road. Logistics networks, trying to optimize delivery routes or supply chains across thousands of variables simultaneously, face a similar wall. In every one of these fields, the pattern is the same. Classical AI can get you remarkably far, often far enough to be genuinely useful. But there's a point where the sheer scale of possible combinations becomes so vast that no amount of classical computing power, no matter how cleverly engineered, can fully explore it. That is precisely the point where quantum computing stops being a theoretical curiosity and starts becoming the only realistic path forward. So where does that leave us right now in this moment? We're not living in a world where quantum computers have replaced AI, and we're probably not going to be living in that world anytime soon. But we are living in a world where the old assumption, the one that said AI's potential, is essentially limitless as long as you keep feeding it more data and more classical computing power, has been proven wrong in specific, documented, repeatable ways. A quantum computer helped a language model answer questions correctly that its classical version got wrong. A quantum processor completed in 2 hours what would have taken a classical supercomputer over 3 years. A quantum-enhanced approach gave AI a level of stability in predicting chaotic systems that classical methods simply couldn't match, while using a fraction of the memory. And in some of the most fundamental mathematical tasks underlying machine learning itself, researchers have proven, not suggested, proven, that quantum systems hold an advantage. Classical machines cannot close, no matter how much hardware you throw at the problem. These aren't rumors. They aren't marketing claims from companies trying to hype their next product launch. They're documented results from research institutions and technology companies willing to publish their methods and their data for other scientists to scrutinize and attempt to replicate. What makes this moment genuinely fascinating isn't that one technology has beaten another. It's that we are watching, in real time, the boundaries of what's computationally possible get redrawn, not through incremental improvement, but through the introduction of an entirely new way of processing information. For decades, computing has meant one thing: bits moving through classical circuits, one operation after another, however fast we could make the hardware. Quantum computing breaks that assumption at the root. And every time it demonstrates an advantage like the ones we've just walked through, it's a reminder that the future of computing was never guaranteed to look like a bigger, faster version of what we already have. It might look like something else entirely, something built on superposition and entanglement instead of transistors and silicon, something that doesn't just run AI faster, but hands AI capabilities it structurally could never have reached on its own. The scientists working at the edge of this field aren't claiming to have all the answers yet. Error correction remains a massive engineering challenge. Scaling these systems up to thousands or millions of reliable qubits remains, for now, a work in progress. But the proof, the actual experimental, peer-reviewed, independently scrutinized proof, is no longer theoretical. It's sitting in research papers, published results, and machines running in labs right now, quietly doing things that classical artificial intelligence, for all its remarkable progress, simply cannot do on its own. And if the last few years taught us anything about how quickly this field can move once a real advantage is proven, then whatever comes next probably won't take as long as we think. The wall AI once seemed destined to climb forever has a crack in it now, and that crack is only going to widen from here.